Hello there and welcome to Deep Sleep Seas. I'm so glad you found your way here. Maybe you've been curious about the hidden landscapes beneath the waves, or perhaps you're the kind of person who finds peace in learning about the quiet places where few have ever ventured. Either way, tonight's journey takes us to one of Earth's most abundant yet least known landscapes, a place where time moves differently, where the weight of the ocean presses down through miles of darkness, and where gentle hills rise and fall across distances that would dwarf entire mountain ranges on land. You've got nothing to do but rest. Let your thoughts drift like sediment falling through deep water. Let your breathing slow to match the patient rhythm of ocean currents that have flowed for millions of years. Because tonight we're descending to the Abyssal Hills, soft landscapes sculpted by time itself, hidden beneath the deepest waters of the world's oceans. These are not the mountains you know from postcards or hiking trails. They don't pierce the sky or catch the morning light. Instead, they lie in absolute darkness, 3 to 4 miles beneath the surface, covered by sediments that have been falling grain by grain for longer than humans have walked the earth. They are the most common landform on our planet, covering roughly 70% of the ocean floor, more abundant than any desert, any forest, any plain you've ever seen.
And yet,
until very recently, we barely knew they existed. They are the quiet undulations of the deepest sea, the forgotten topography of a world we've only just begun to map. And tonight, as your eyes grow heavy and your mind begins to wander, we'll explore them together, slowly, gently, and without hurry. Before we begin, if you find these journeys into the ocean's mysteries relaxing, consider subscribing so you don't miss the next deep voyage. Now let's descend into the darkness, where the Abyssal Hills await. The Abyssal Hills are everywhere beneath the sea, yet nowhere you can see. If you could drain all the water from the world's oceans and walk across the exposed seafloor, you would find yourself in a landscape unlike anything on the surface of our planet. Not the jagged peaks of underwater volcanoes or the sheer drops of ocean trenches, but something softer, something more repetitive, something strangely ordered. You would see endless rows of gentle hills, aligned in parallel bands like furrows in an immense field, stretching to the horizon in every direction. Some would rise only a few dozen meters above the surrounding seafloor, others would tower several hundred meters high. But all of them would share the same curious feature. They would all run in the same direction, parallel to invisible lines that mark where the Earth's crust is being torn apart and remade. These are the Abyssal Hills, and they cover more of Earth's surface than all the continents combined. They are found in every ocean basin, beneath every major sea, from the cold waters of the Arctic to the warm currents of the equator, from the youngest seafloor near volcanic ridges to the oldest crust at the edges of continents. The Abyssal Hills persist. They are the dominant feature of the deep ocean floor, the baseline topography against which everything else is measured. And yet, for most of human history, we had no idea they were there. The ocean kept its secret well. It wasn't until the middle of the 20th century, when scientists began using sonar and other acoustic instruments to map the seafloor, that the true nature of the abyssal landscape began to reveal itself. Before that, people imagined the deep ocean floor as essentially flat, a vast muddy plain stretching uninterrupted across the bottom of the sea. Early depth soundings, taken laboriously with weighted lines, seemed to confirm this idea. The depths were remarkably consistent across large areas, but those early measurements were crude, and they missed the subtle variations that define the abyssal world. When better instruments became available, the picture changed dramatically. In the 1940s and 50s, oceanographic research vessels equipped with continuous echo-sounding devices began to trace the contours of the seafloor in unprecedented detail. What they discovered was astonishing. The ocean bottom was not flat at all. It was covered with hills, thousands upon thousands of them, arranged in orderly rows, rising and falling in a pattern that repeated across entire ocean basins. These hills were typically a few kilometers wide and a few hundred meters high, though their exact dimensions varied depending on where they were found and how they had formed. They were elongated rather than round, stretched out parallel to the mid-ocean ridges where new seafloor is born, and they were quite simply everywhere, covering an area so vast that it defied easy comprehension. Scientists gave them the name Abyssal Hills, from the Latin word for deep. The term was simple, almost understated, for features that turned out to be the most abundant landform on the planet. Not mountains, not peaks, just hills, soft, repetitive, and somehow humble despite their ubiquity. But as researchers studied them more closely, they realized these humble hills held clues to one of the most fundamental processes on Earth, the movement of tectonic plates and the creation of new oceanic crust. The abyssal hills do not exist by accident. They are not random features scattered across the seafloor like boulders dropped by some cosmic hand. Instead, they are the direct product of forces deep within the Earth, forces that shape continents, trigger earthquakes, and drive the slow drift of land masses across the globe. To understand how the abyssal hills form, you must first understand the mid-ocean ridges, the underwater mountain ranges where the Earth's crust is being pulled apart. The mid-ocean ridges form a continuous chain more than 60,000 kilometers long, winding through all the major ocean basins like the seam on a baseball. These ridges mark the boundaries between tectonic plates, the massive slabs of rock that make up the Earth's outer shell. At the ridges, two plates are moving away from each other, creating a gap. As they separate, hot molten rock from the mantle below rises to fill the space. This magma cools and solidifies, forming new oceanic crust. The process is called seafloor spreading, and it has been going on for hundreds of millions of years. But seafloor spreading is not a smooth, steady process. It happens in fits and starts, driven by a complex interplay of volcanic eruptions and tectonic faulting. As the new crust cools and moves away from the ridge, it undergoes tremendous stress. The rock stretches and fractures, creating a network of faults, cracks where one block of crust has slipped relative to another. These are normal faults, where the crust is being pulled apart rather than pushed together. The blocks of crust tilt and rotate as they slip, creating the characteristic undulating topography of the abyssal hills. Imagine the seafloor as a series of giant dominoes, each one tilted at a slight angle, arranged in long parallel rows. As the crust spreads, new dominoes are constantly being added at the ridge, while older ones are carried away on either side. Each domino represents a fault block, a slice of oceanic crust bounded by fractures. Over time, these blocks become the abyssal hills, frozen in place as they move away from their birthplace at the ridge. The result is a washboard pattern, a series of ridges and valleys that stretch across the seafloor for thousands of kilometers. The exact shape and size of the abyssal hills depend on how fast the seafloor is spreading. At fast-spreading ridges, like the East Pacific Rise, where the plates are pulling apart at rates exceeding 10 centimeters per year, the hills tend to be low and closely spaced. There is abundant magma supply, and the new crust forms relatively smoothly. The faulting is less pronounced, and the resulting hills are gentle swells, rarely rising more than 100 meters above the surrounding seafloor. At slow-spreading ridges, like the Mid-Atlantic Ridge, where the plates separate at rates of just a few centimeters per year, the hills are taller and more widely spaced. The magma supply is limited, and the faulting is more dominant. The blocks of crust tilt more dramatically, creating hills that can rise several hundred meters high. This relationship between spreading rate and hill morphology is one of the key insights that scientists have gained from studying the abyssal hills. It tells us something fundamental about how new oceanic crust is created, how the balance between volcanic activity and tectonic deformation shapes the seafloor. It also provides a kind of geological record, a way to read the history of seafloor spreading by examining the patterns of hills and valleys on the ocean floor. But volcanic activity also plays a role in shaping the abyssal hills, particularly at faster spreading ridges. As magma erupts at the mid-ocean ridge, it doesn't always spread out evenly. Sometimes it piles up in small volcanic edifices, little hills of solidified lava that add to the topographic relief. These volcanic hills are often asymmetric, with one side steep and the other gentle, reflecting the direction of lava flow. Over time, they can be offset and tilted by faulting, becoming part of the larger pattern of abyssal hills. The interplay between volcanism and tectonics creates a complex landscape, one that varies from place to place depending on the local conditions of the ridge where the crust was formed. What's remarkable is how consistent the abyssal hills are across such vast distances, despite the variations in spreading rate and magma supply, despite the differences between ocean basins and the passage of millions of years. The basic pattern remains the same. Parallel rows of elongated hills, aligned perpendicular to the direction of plate spreading. It's as if the Earth has a preferred way of breaking its crust, a fundamental pattern that emerges whenever tectonic plates pull apart. Scientists are still working to understand why this pattern is so universal, what physical principles govern the formation of the hills, but there's no doubt that it's one of the most characteristic features of the ocean floor, a signature of the tectonic forces that shape our planet. As the newly formed crust moves away from the mid-ocean ridge, it begins a long, slow journey across the ocean basin. The abyssal hills that formed at the ridge are carried along with it, riding on the tectonic plate like passengers on a conveyor belt. This journey can last for tens of millions of years, and during that time, the hills undergo gradual changes. The rock cools and contracts, causing the seafloor to subside, to sink deeper into the ocean. The hills become less pronounced as thermal contraction reduces their relief. At the same time, sediments begin to accumulate on the seafloor, slowly burying the hills under layers of fine particles. These sediments come from many sources. Some are the remains of tiny marine organisms, plankton and algae that lived in the sunlit waters near the surface and sank to the bottom when they died. Their shells and skeletons, made of calcium carbonate or silica, accumulate in layers called oozes, thick deposits of biogenic material that can cover large areas of the seafloor. Other sediments are made of clay particles, fine mineral grains that were eroded from continents and carried out to sea by rivers and winds. Over time, these particles settle out of the water column, drifting down through miles of ocean to land gently on the abyssal hills. The process of sedimentation is incredibly slow. In the deepest parts of the ocean, far from continents and river mouths, the rate of sediment accumulation is typically just a few millimeters per 1,000 years. At that rate, it would take millions of years to bury a hill several hundred meters high. And yet, given enough time, that's exactly what happens. The sediments pile up, layer upon layer, gradually filling in the valleys between the hills and smoothing out the seafloor. Eventually, if the sediment supply is sufficient, the hills are completely buried, and the undulating topography is replaced by a flat, featureless plain. This is how abyssal plains are formed, the smooth, flat regions that cover large areas of the ocean floor. They are not separate features from the abyssal hills, but rather the same landscape hidden beneath a thick blanket of sediment. Beneath every abyssal plain lies a buried topography of hills and valleys, the original seafloor created at the mid-ocean ridge. Seismic profiling, which uses sound waves to image the layers beneath the seafloor, has confirmed this. The profiles show the undulating basement rock, the abyssal hills, overlain by horizontal layers of sediment that smooth out the surface. The amount of sediment covering the seafloor varies greatly from one ocean basin to another, and this has a profound effect on the visibility of the abyssal hills. In the Atlantic and Indian Oceans, which receive large amounts of sediment from the surrounding continents, the abyssal hills are often deeply buried. The seafloor is dominated by smooth abyssal plains, vast flat areas that give little hint of the rugged topography beneath. In the Pacific Ocean, by contrast, sediment supply is more limited. The Pacific is surrounded by deep ocean trenches where sediments are trapped and subducted into the mantle, preventing them from reaching the abyssal depths. As a result, between 80 and 85% of the Pacific seafloor is covered by exposed abyssal hills, their undulating surfaces visible and largely unburied. This difference in sediment coverage has important implications for our understanding of the ocean floor. The Atlantic and Indian Oceans, with their extensive abyssal plains, were once thought to represent the typical state of the deep sea, but as scientists explored the Pacific more thoroughly, they realized that the exposed abyssal hills of the Pacific were actually closer to the norm. The smooth plains of the Atlantic were the exception, the result of unusually heavy sedimentation rather than the baseline condition. In a sense, the Pacific Ocean gives us a clearer view of what the seafloor really looks like, what it looks like before the sediments arrive to hide it. The abyssal hills are found in every major ocean basin, but their distribution is not uniform. They are most abundant near the mid-ocean ridges, where the seafloor is youngest and the hills are still relatively fresh and unburied. As you move away from the ridge, the hills become older and are progressively covered by sediment. In some regions, particularly near the continental margins, the hills are completely buried beneath thick accumulations of sediment that have been carried out from land by turbidity currents, dense underwater avalanches of sediment-laden water that flow down the continental slopes and spread out across the abyssal floor. The global coverage of abyssal hills is staggering. They are estimated to cover somewhere between 20 and 30% of the entire ocean floor if you count only the exposed hills, and up to 70% if you include the buried hills beneath the abyssal plains. That means they cover more area than all the continents combined. In fact, the abyssal hills are the single most extensive landform on Earth, far more common than any feature you can see on the surface. And yet, most people have never heard of them. They are the hidden majority, the forgotten landscape of a planet that is mostly water. The abyssal hills are not just a curiosity for geologists and oceanographers. They play important roles in the functioning of the ocean itself, roles that scientists are only beginning to understand. One of the most significant is their effect on ocean circulation and mixing. The hills create roughness on the seafloor, and this roughness interacts with the currents that flow across the abyss. As water moves over the hills, it is forced to rise and fall to accelerate and slow down. These changes in flow generate turbulence, the chaotic motion of water at small scales, and turbulence leads to mixing. Mixing is crucial in the ocean because it helps to distribute heat, salt, nutrients, and other properties throughout the water column. Without mixing, the ocean would stratify, with warm water sitting on top of cold water and no way to transfer heat downward. The deep ocean would become isolated and stagnant, but mixing driven by internal waves and turbulence keeps the waters connected, allowing heat to penetrate to the abyss and cold water to rise toward the surface. This mixing is an essential part of the global ocean circulation, the great conveyor belt that transports heat around the planet and regulates Earth's climate. The abyssal hills contribute to this mixing in a very specific way. They generate internal tides, waves that travel not on the surface of the ocean but within its depths, along the boundaries between layers of water with different densities. These internal waves are created when tidal currents, the regular back and forth motion of water driven by the gravitational pull of the moon and sun, flow over the rough topography of the abyssal hills. As the water is forced up and over the hills, it oscillates, creating waves that propagate away from the hills and eventually break down into turbulence. Internal tides are a major source of energy for mixing in the deep ocean. Scientists estimate that the abyssal hills contribute a significant fraction of the total internal tide generation globally, perhaps as much as 10% or more. This might not sound like a lot, but in the context of the vast, energy-starved deep ocean, it's a substantial contribution. The energy that goes into generating internal tides is ultimately dissipated as heat through turbulent mixing, and this mixing helps to maintain the structure and circulation of the deep ocean. Recent satellite missions have provided new insights into the role of abyssal hills in generating internal tides. The Surface Water and Ocean Topography Satellite, known as SWOT, uses advanced radar to measure the height of the sea surface with extraordinary precision. Because seafloor features like abyssal hills exert a gravitational pull that creates tiny bumps in the sea surface above them, SWOT can detect these features and map them in detail. The data from SWOT have revealed thousands of previously unknown abyssal hills and have allowed scientists to estimate their contribution to internal tide generation with greater accuracy than ever before. What they've found is that the abyssal hills, despite their modest size, have an outsized impact on ocean dynamics. The hills are small enough that they generate high-mode internal tides, waves with short wavelengths and rapid oscillations. These high-mode waves don't travel far from their source. Instead, they break down into turbulence near the hills themselves, contributing to local mixing. This near-field mixing, as it's called, is thought to be particularly important over the rough topography of mid-ocean ridges, where the abyssal hills are most abundant and the internal tide generation is strongest. But the abyssal hills also affect the ocean in more subtle ways. They create variability in the seafloor environment, introducing differences in depth, slope, and sediment type that can influence the organisms living there. The deep ocean is often thought of as a uniform, featureless environment, a place where conditions are essentially the same everywhere. But the abyssal hills show that this is not the case. Even modest changes in topography, just a few hundred meters of relief, can create significant differences in the physical and biological conditions on the seafloor. Studies of abyssal hills in the North Atlantic, particularly around the Porcupine Abyssal Plain, have revealed that the hills support higher biomass of large organisms than the surrounding flat areas. The hills have more food available, in the form of particulate organic matter that settles from the surface, and this extra food supports more animals. The hills also have different sediment characteristics, with coarser particles and less organic content, likely because of the stronger currents that flow over them. These environmental differences lead to distinct biological communities, with different species compositions and diversity patterns on the hills compared to the plains. The enhanced biomass on the abyssal hills is striking. Studies have found that the total biomass of megafauna, large animals visible in seafloor photographs, can be 2 to 3 times higher on the hills than on the adjacent plains. This is a much larger difference than would be predicted based on the depth alone. It suggests that the topography of the hills creates favorable conditions for life, perhaps by concentrating food or by providing more varied habitats. The hills are not just passive features, they actively shape the ecology of the deep sea. This ecological significance is particularly important when we consider the vast extent of the abyssal hills. If even a small fraction of the global abyssal seafloor is covered by hills, and if those hills support higher biodiversity and biomass than the surrounding plains, then the total contribution of the hills to deep-sea biodiversity could be enormous. The abyssal hills might act as biodiversity hotspots, regions where life is more abundant and diverse than average, scattered across the ocean floor in a network of elevated terrain. Of course, life in the abyssal hills is still life in the deep sea, and that means it is adapted to some of the most extreme conditions on Earth. The water temperature is near freezing, just a few degrees above 0 Celsius. The pressure is crushing, hundreds of times greater than at the surface, and there is no sunlight, none at all. The abyssal hills lie far below the photic zone, the upper layer of the ocean where photosynthesis can occur. The only light that reaches these depths comes from bioluminescent organisms, creatures that produce their own light through chemical reactions in their bodies. Food is scarce in the abyss. The primary source of energy is the rain of organic particles from above, the bits and pieces of dead organisms that sink down from the surface waters. This marine snow, as it's called, is the main food supply for most deep-sea life, but it's a meager supply spread thin across vast areas. The organisms that live on the abyssal hills must eke out an existence on these limited resources, scraping up whatever they can find, filtering particles from the water, or scavenging on the occasional larger food fall, like the carcass of a whale or a large fish. Despite these challenges, The abyssal hills are home to a surprising variety of life. There are brittle stars and sea cucumbers, small crustaceans and worms, delicate corals and sponges. There are foraminifera, single-celled organisms that build tiny shells, and bacteria that break down organic matter in the sediments. Each species has its own adaptations for surviving in this harsh environment, its own way of finding food, avoiding predators, and reproducing in the cold, dark depths. One of the remarkable things about abyssal life is how slowly it operates. In the cold water, metabolic rates are low, and organisms grow and reproduce at a glacial pace. Some deep-sea fish can live for decades or even centuries. Some corals can live for thousands of years. Time moves differently in the abyss, measured not in seasons but in epochs. The abyssal hills themselves are ancient, millions of years old, and the communities that live on them have evolved over similarly vast timescales. The exploration and mapping of the abyssal hills is a relatively recent achievement, made possible by advances in technology that allow us to study the deep ocean in ways that were unimaginable just a few decades ago. For most of human history, the deep sea was a place of mystery and speculation, a realm beyond the reach of our senses and instruments. Early explorers lowered weighted lines over the side of their ships to measure depth, a laborious process that could take hours and provided only a single data point. It wasn't until the development of echo-sounding sonar in the early 20th century that scientists could begin to map the seafloor continuously as their ships moved across the ocean. The first comprehensive maps of the ocean floor, created in the 1950s and 60s by pioneers like Marie Tharp and Bruce Heezen, revealed the existence of the abyssal hills and showed their global extent. But these early maps were based on widely spaced ship tracks and lacked the detail needed to study the hills in depth. It wasn't until more advanced sonar systems were developed, systems that could map swaths of seafloor hundreds of meters wide with meter-scale resolution, that the true complexity of the abyssal hill landscape became clear. Today, scientists use a variety of tools to study the abyssal hills. Multi-beam sonar systems mounted on research vessels create detailed three-dimensional maps of the seafloor, revealing the shape and structure of individual hills. Autonomous underwater vehicles, or AUVs, can dive to the seafloor and collect high-resolution images and measurements over small areas, and satellite altimetry, like the data from the SWAT mission, provides a global view of seafloor topography by measuring the subtle variations in sea surface height that result from the gravitational pull of underwater features. Each of these methods has its strengths and limitations. Ship-based sonar provides excellent detail but is slow and expensive, limited to the areas that research vessels can reach. AUVs can get close to the seafloor and see fine-scale features, but they cover only small areas and require extensive logistical support. Satellite altimetry can survey the entire globe quickly, but its resolution is limited, and it can only detect features that are large enough to produce a measurable gravitational signal. By combining these methods, scientists are gradually building a more complete picture of the abyssal hills, their distribution, their characteristics, and their role in the ocean system. One of the most exciting recent developments is the ability to use satellite data to detect abyssal hills that are only a few kilometers across, much smaller than was previously possible. The SWAT satellite, launched in late 2022, has demonstrated that it can measure sea surface height with centimeter-level accuracy, sensitive enough to pick up the tiny bumps caused by the gravitational pull of small seafloor features. This capability has allowed researchers to map tens of thousands of previously unknown abyssal hills, particularly in remote areas of the ocean that have never been surveyed by ships. These new maps are revealing patterns that were not apparent before. They show that the orientation and spacing of the abyssal hills vary in systematic ways, reflecting changes in the spreading rate and magma supply at the mid-ocean ridges where the hills were formed. They show that in some regions the pattern of hills abruptly changes direction, indicating a shift in the motion of the tectonic plates. And they show that the abyssal hills are more variable and complex than the simple washboard model would suggest. with hills that branch, merge, and curve in ways that hint at a richer underlying geology. The mapping of the abyssal hills is not just an academic exercise. It has practical implications for our understanding of the ocean and for human activities in the deep sea. Accurate maps of seafloor topography are needed for navigation, especially for submarines and other underwater vehicles. They are needed for laying undersea cables, the fiber optic lines that carry internet and telecommunications traffic across the ocean, and they are needed for assessing the environmental impact of deep-sea mining, an emerging industry that aims to extract valuable minerals from the seafloor. Deep-sea mining is particularly relevant to the abyssal hills and plains because some of the most sought-after mineral resources are found there. Polymetallic nodules, potato-sized lumps of manganese, iron, nickel, cobalt, and copper, lie scattered on the seafloor in certain areas, particularly in the Pacific Ocean. These nodules form slowly over millions of years, accumulating metals that precipitate from seawater. They are most abundant in regions where sedimentation rates are low, where the nodules have time to grow without being buried. The abyssal hills and plains are prime locations for these nodules, and there is growing interest in mining them for their metal content. But deep-sea mining raises serious environmental concerns. The process of collecting the nodules involves dragging large machines across the seafloor, disturbing the sediments and destroying the habitats of the organisms that live there. The sediment plumes created by mining can spread over vast areas, smothering communities far from the mining site. And because the deep ocean is so poorly understood, and because the organisms there grow and reproduce so slowly, it's difficult to predict how long it would take for the ecosystem to recover, if it can recover at all. The abyssal hills add another layer of complexity to these concerns. Because the hills support higher biodiversity and biomass than the surrounding plains, they might be particularly sensitive to disturbance. Mining on or near the hills could have a disproportionate impact on deep-sea life. And because the hills are so widespread, covering such a large fraction of the ocean floor, it's nearly impossible to avoid them entirely. Any large-scale mining operation in the abyssal zone is almost certain to affect abyssal hill habitats. These issues are still being debated by scientists, policymakers, and the mining industry. The International Seabed Authority, the organization responsible for regulating deep-sea mining in international waters, is working to develop rules that will minimize environmental damage. But there is much that we still don't know about the abyssal hills, about the life they support, and about how that life would respond to disturbance. The more we learn about these hidden landscapes, the better equipped we'll be to make informed decisions about how to use and protect them. The abyssal hills are also a window into the geological history of the Earth, because they form at mid-ocean ridges and then move away as the seafloor spreads. The hills carry a record of the conditions at the ridge when they were created. By studying the size, shape, and spacing of the hills, scientists can infer the spreading rate, the magma supply, and the tectonic stress regime at the time of formation. This information can be used to reconstruct the history of seafloor spreading, to understand how the ocean basins have evolved over millions of years. One of the intriguing questions about abyssal hills is whether their formation is influenced by processes other than the steady spreading of the seafloor. For example, some researchers have proposed that variations in magma supply driven by long-term climate cycles might affect the size and spacing of the hills. The idea is that during ice ages, when sea level is low, the reduced pressure on the ocean floor could alter the melting and eruption of magma at the mid-ocean ridges, leading to pulses of volcanic activity that would be recorded in the spacing of the abyssal hills. This hypothesis has been the subject of debate. Some studies have found patterns in the spacing of abyssal hills that appear to match the timescales of Earth's orbital cycles, the Milankovitch cycles that drive ice ages, but other studies have found no such correlation, and numerical models suggest that the seafloor is too stiff to deform in response to such small variations in magma supply. The jury is still out on whether climate cycles influence abyssal hill formation, but the question highlights the interconnectedness of Earth's systems the ways in which processes in the atmosphere, ocean, and solid Earth can interact over long timescales. What is clear is that the abyssal hills are ancient. The oldest seafloor on Earth is about 200 million years old, and the abyssal hills on that seafloor formed at the mid-ocean ridges 200 million years ago. That's older than the Atlantic Ocean, older than the dinosaurs, older than the breakup of the supercontinent Pangaea. The hills have been sitting on the seafloor, slowly accumulating sediment for an almost incomprehensible span of time. They have witnessed the opening and closing of ocean basins, the drift of continents, the rise and fall of species. They are, in a very real sense, the memory of the Earth, carved into rock and carried across the ocean floor. As the hills age, they subside. The cooling of the oceanic lithosphere causes it to contract and become denser, and as it does, it sinks deeper into the mantle. This thermal subsidence is a gradual process, occurring over tens of millions of years, but it has a profound effect on the seafloor. The youngest seafloor, near the mid-ocean ridges, is relatively shallow, typically 2 to 3 kilometers below sea level. The oldest seafloor, near the continental margins, is much deeper, 5 to 6 kilometers or more. The abyssal hills subside along with the rest of the seafloor, their relief gradually decreasing as the underlying rock contracts. At the same time, the sediments continue to accumulate. The combined effect of subsidence and sedimentation is to bury the hills, to smooth out the seafloor, and create the flat abyssal plains. In regions where sediment supply is high, this process can be completed relatively quickly, in geologic terms, within a few tens of millions of years. In regions where sediment supply is low, the hills can remain exposed for much longer, surviving for 100 million years or more. The life cycle of the abyssal hills, from their formation at the mid-ocean ridge to their eventual burial beneath the abyssal plains, is a story of transformation and slow erasure. It's a story written in sediment and stone, in the layers that accumulate grain by grain, in the faults that slice through the rock, in the gentle curves of the hills themselves. It's a story that spans millions of years, but it's happening all around us, beneath the waves, in the quiet darkness of the deep sea. And that brings us to the heart of what makes the abyssal hills so remarkable. They are the most abundant landform on Earth, and yet they are almost entirely hidden from view. They cover more area than any other feature on the planet's surface, and yet most people will never see them, never know they exist. They are the quiet majority, the forgotten landscape, the baseline topography of a world that is mostly water. In a way, the abyssal hills are a humbling reminder of how much of our planet remains unexplored. We have mapped the surfaces of the Moon and Mars in greater detail than we have mapped the ocean floor. We have sent spacecraft to the outer reaches of the solar system, but we have barely scratched the surface of the deep sea. The abyssal hills, for all their abundance, are still largely unknown to us. We know they're there. We know how they form. We know roughly how many there are. But we don't know them in the way we know the mountains and valleys of the land. We don't have names for individual hills. We don't have photographs of most of them. We don't know what lives on them, what secrets they hold. This is changing, slowly, as technology improves and our ability to explore the deep ocean expands. Each new map, each new survey, adds to our knowledge. Each discovery reveals a little more of the hidden landscape beneath the waves, but the abyssal hills will likely remain mysterious for a long time to come. The ocean is vast, and the depths are deep, and the resources needed to explore them thoroughly are immense. For now, the abyssal hills remain mostly out of reach, a landscape we can sense but not see, a world we can imagine but not visit. And perhaps there's something fitting about that. The abyssal hills are not meant to be seen by human eyes. They exist in darkness, in a realm where light does not penetrate. They are shaped by forces that operate on timescales far longer than a human lifetime, forces that move continents and create oceans. They are home to creatures that have never seen the sun, that live their entire lives in the cold and the dark. The abyssal hills belong to the ocean, not to us. They are a reminder that there are places on Earth that are still wild, still unknown, still beyond our control. As we rest tonight, as our breathing slows and our minds begin to drift, we can imagine those hills stretching away into the darkness, row after row of gentle undulations, covered by sediments that have been falling for millions of years. We can imagine the currents flowing over them, the internal tides rising and falling, the creatures moving slowly across their flanks. We can imagine the vastness of it all, the sheer scale of the hidden landscape that lies beneath the sea. The abyssal hills are not dramatic. They don't inspire the same awe as a towering mountain or a deep trench. They are subtle, repetitive, almost mundane in their simplicity. But there is beauty in that simplicity, in the endlessly repeating pattern, in the quiet persistence of features that have endured for millions of years. The abyssal hills are proof that the Earth is patient, that geological processes unfold on timescales that dwarf human comprehension, that the most abundant features on our planet are also the most hidden. And so we leave them there, in the darkness, rising and falling across the ocean floor. We leave them to their slow transformation, to the accumulation of sediments and the passage of time. We leave them to the creatures that call them home, to the currents that flow over them, to the internal tides that they generate. The abyssal hills will be there long after we are gone, long after our cities have crumbled and our names have been forgotten. They are the patient landforms, the soft landscapes sculpted by time, the hidden majority of a planet covered by water. Tonight, as you drift towards sleep, you might think of them. You might imagine the weight of the ocean pressing down, the absolute darkness, the cold that never changes. You might picture the gentle hills rising and falling, the sediments settling softly, the currents moving in slow circles. You might feel a kind of peace in knowing that there are places like this, places so vast and so remote that they exist almost beyond imagination, places that remind us how little we know and how much there is still to discover. The abyssal hills are the ocean's secret, kept for millions of years, revealed only recently by our improving technology. They are a landscape we are only beginning to understand, a feature so common that it defines the ocean floor, yet so hidden that it remained unknown until we developed the tools to see it. They are the soft undulations of the deepest sea, shaped by the splitting of the Earth's crust, buried slowly by the rain of sediment, home to creatures that live in eternal night. In the grand scheme of Earth's geography, the abyssal hills are ordinary. They are not the highest or the deepest, not the most dangerous or the most beautiful. They are simply the most abundant, the baseline, the default state of the ocean floor. And yet, in their very ordinariness, they are extraordinary. They remind us that the Earth is a dynamic planet, constantly changing, constantly creating and destroying landscapes. They remind us that the ocean is not a featureless void, but a complex environment with its own topography, its own geology, its own ecology. They remind us that there is still so much we don't know, so much that remains hidden beneath the waves. So tonight, rest easy knowing that far beneath the surface, in the darkness and the cold, the abyssal hills persist. They are the unsung landscapes of the ocean floor, the quiet majority, the soft forms sculpted by time itself. They will be there tomorrow, and the day after, and for millions of years to come. They are patient, they are enduring, and they are waiting, in the darkness, for us to discover their secrets. Sleep well, knowing that the ocean holds worlds we have barely begun to explore. Let your mind drift down through the dark water, past the photic zone, past the twilight zone, down to the abyssal depths where the hills rise and fall in endless rows. Let the weight of the water above you be a comfort, a reminder that there are forces greater than ourselves, processes that operate on scales we can barely comprehend. The abyssal hills are there, always there, a constant presence in the hidden landscape of the sea. And now the darkness deepens, the current slows, the sediments continue their patient fall. You are part of this world, even if you will never see it, even if it remains forever hidden from your eyes. The abyssal hills are the foundation of the ocean, the base layer upon which everything else is built. They are the Earth's memory, written in rock and carried across the seafloor by the slow march of tectonic plates. They are the most abundant landform on our planet, and they are the most forgotten, but they are there, always there, beneath the waves. As you rest, as your thoughts grow quiet and your breathing becomes soft, you can carry this image with you. The endless rows of hills, stretching to a horizon that doesn't exist in the darkness, the gentle slopes, worn smooth by currents and covered by sediments, the creatures moving slowly, carefully, in search of food, the internal tides rising and falling, invisible waves in the deep, the weight of the ocean pressing down, holding everything in place, the patience of geological time, measured not in seconds or years but in millions of years, in the slow dance of continents, in the opening and closing of ocean basins. The abyssal hills are ordinary miracles. They are the proof that the extraordinary can be hidden in plain sight, or rather hidden in the darkness where no sight is possible. They are the landscapes we will never walk, the vistas we will never see, the mountains we will never climb, and yet they are real as any mountain range on land, as real as the ground beneath your feet. They are part of Earth's story, part of the living, breathing, changing planet that we call home. Tonight they are at rest, as you are at rest. The currents flow gently over them, the sediments fall softly upon them. The creatures navigate their slopes with practiced ease, and somewhere deep beneath the waves, in the absolute darkness of the abyss, a new abyssal hill is forming at a mid-ocean ridge, born from the splitting of the crust, destined to join the millions that have come before it, destined to ride across the ocean floor for tens of millions of years, slowly subsiding, slowly being buried, slowly fading into the geological record. This is the way of the abyssal hills. This is their story, quiet and long and patient. And now, as you drift towards sleep, their story becomes part of yours. You have traveled with them tonight from their birth at the ridges to their burial beneath the plains. You have seen them with your mind's eye, even though they exist in a place where no eye can see. You have understood, if only for a moment, what it means for something to be both abundant and hidden, both ordinary and extraordinary, both simple and profoundly complex. Rest now. Let the abyssal hills carry you into dreams. Let the weight of the ocean be a comfort, a reminder that there are depths we cannot plumb, mysteries we cannot solve, wonders we cannot fully comprehend. The hills will be there when you wake, as they have been for millions of years, as they will be for millions more. They are the patient landforms, the soft landscapes, the gentle undulations of the deepest sea. They are the ocean's secret, and tonight you have shared in that secret. Good night. Sleep softly. Dream of deep water and endless hills of currents and sediments, of time measured in millions of years. Dream of the hidden majority, the forgotten landscape, the most abundant landform on Earth. The abyssal hills await, in the darkness, forever patient, forever enduring. And in your dreams, you might just catch a glimpse of them, rising and falling beneath the waves, soft forms sculpted by time, the quiet heartbeat of the ocean floor.